Alrighty. I'm going to have to send out a message about people attending class, I think. Before I get started, any questions? We got homework due on Tuesday. So, any questions on that? Or what I expect from the answers?
How long do you want exams to be?
I want them to be long enough to contain enough content to satisfy me. No, I mean, I want them to, like I said, contain an answer that is not really just. Okay, every question that a book asks usually has a sentence involved in the text that corresponds to the answer. So I don't want that. Longer than that. It should contain something regarding what we've discussed in class, issues that you think are related. Really, any of the questions in the book are launching points to talking about operating systems on end for hours. So I don't expect that either. So something in between. So the main thing is I want just demonstration that you know what the concept's related to, issues that are involved. One of the things that that a lot of questions don't explicitly ask for are like if it says something along the lines of how is this usually handled or whatever, you can explain how it's usually handled. What's not necessarily asked for is what are the trade-offs with that. We've seen that everything in operating system design, as with most programming and things like that, is a trade-off between different goals and things like that. So some demonstration of that, saying I know what the goal is, why they do it that way, type of thing. So like one of the questions, did I ask the short, medium, and long-term scheduling question, I think? I'm not sure if I remember if I asked that. In chapter 3.
Oh, I haven't been
I mean, obviously you can sit there and say, well, short-term scheduling does this, long-term scheduling does this, medium-term scheduling does this. You need to go a little bit further and say, why have these 3 different scheduling problems? Why do we have different approaches to each one? What's critical in each one? What's not critical in another? So show how they're the pros and cons to each one are kind of contrasting each other, and that's why they break it up into separate goals, that kind of thing. Okay? But somewhere in the book, there's going to be a paragraph that says short-term scheduling does this, medium-term scheduling does this, and long-term scheduling does this. So you just go a little bit beyond that, and it shows that demonstrates that you kind of mastered some of that information. Okay. Any other questions? Any problems with WebCT or anything?
Yeah, I'm having problem
Logging on? Okay. Have you not logged on to WebCT before?
I did. Just yesterday, even though the same.
You've logged on again. You've logged on before this semester.
This semester earlier, I looked at your notes. All of a sudden yesterday, it didn't work.
I don't know who's support for WebCT.
Yeah, that's the problem.
Is it Library Sal? Okay. Yeah, I mean, you might have to do that, but I mean, WebCT, occasionally I always get these pop-ups that they're doing maintenance at one time or another, so I don't know if it's related to that or anything. If it seems just you can't log in, you have to go to support. But, because I can't. I don't know why you can't. No, but, so yeah, that's the only thing I can think of. But anybody having trouble with like their browser or Java or anything like that as far as, I know it's been ornery.
You can't get out from the school computer.
I know that's ironic to me. It's like their Java's configured wrong, so you can't get on there. It's good that we're paying for WebCT so that we can have systems even at our own school that can't get on. But okay, we'll continue with chapter 3, processes. We kind of left off last time, getting done with the kind of really under the hood issues with processes, how we do context switches, how we actually accomplish this feature of multiple processes running on the same machine, and some of the issues that come up there. now what we're going to do is kind of get, go up a little level and see kind of, now that we have this mechanism for running multiple processes and things, what do we do with it? How do we get to the end goal of having an operating system running that can, give our users facilities to run programs and things like that? So, a basic mechanism that we kind of created with these concepts was the idea of a process creating another process. Okay? Now that we have multiple processes, we need a way to start creating them. And what's the typical, or at least common way, like if you remember from Unix and systems programming, what's the common way to create another process when you're in a process? Threads are one way. So that's actually a whole other school of processes. Threads are lightweight processes in the fact that they actually run within the process that you create them in, which is very powerful, and we'll see how powerful that is when we talk about some of the limitations of full-blown processes running alongside you. So threading is one way. You create another thread and it will run alongside. What's the more basic kind of general way of creating other processes? Forking. Okay? You have a running program. You make the system call the fork, and then what happens now? What are the problems with creating another thread of execution? You kind of know where all your instructions come from for a program that you're running. It's from the program, right? You run a program, it loads the code into memory and stuff and starts executing. So now, the operating system kind of did that, right? Loaded your program into the process and started running it. Where do we get? What's running when we call fork in the separate process that we created?
What's the question again?
What is running? I have process A. I fork and create process B. What's running in process B? Does fork take any arguments? It doesn't. Fork is just empty parameters, and it actually just returns something. So, from calling fork with nothing, right, with nothing in it, what's running in that process? Is it just sitting there? Does it stop? If it stopped, how do we start it? Any ideas? Anybody remember writing fork programs? When you call fork, what's running in the forked process, and the second process you've created, is an exact duplicate of the process that called it. Yes. Okay. But the difference is in what fork returns. Why do you say no? Or are you saying no, that doesn't seem to accomplish anything?
No, I put it this way, like when you call forking and create a child process, suppose, and that child process, while it's processing something, the parent process is like idle. Wait until
No.
That's what it.
If it's idle, we don't need two processes.
It's probably depending on the child process result or something.
Because if you're just going to wait for the child process to run and wait for its results, why do you need another thread of execution? Right? Yeah.
What's the point?
Okay, so what is the point? Well, as I said, there's one difference. It's what fork returns. What does fork return? Fork returns a process ID. Okay? If you're the parent process A, that's calling fork, what do you think fork returns to you? Right. The child's, it actually returns the child's process ID. Right? If you're the child, what do you return? You actually just return nothing. No, the parent's still there, right? Because we want both of these running at the same time, okay? But the parent gets the child's process ID, and the child gets 0. Okay, so that's enough. But the rest of the process is the same. All the variables that we have in there, the code that's running, all of that's the same. So we still seem to kind of be in the same difficulty in the fact that 2 identical processes running at the same time doesn't really accomplish anything, right? But we do have one difference, and that's that process ID that's returned. So what do? How do you make it so that the program that you're running, that you fork off of, you're not just running 2 of the same program at that point? You are, but how do we make them do different things?
You continue up with the parent one.
By doing what? But if they're the same instructions, how do we do one thing in the parent and another thing in the child? There's a construct in programming that's ideal for this. What is that construct? Here's a hint. If I'm the parent, do this. Otherwise, if I'm the child, do that. So there's if-then, right? Or if-else, or whatever you want to call it. But how do I answer that question if I'm the parent? By what fork return, right? The process ID that fork return. If it returns a 0, you're the child. If it returns a number, you're the parent. In fact, you're the parent and you know what the child's process ID is. So now, even though we're running 2 of the same program, we have one variable that's different in the 2 programs that we can now differentiate. So we can have a block of stuff, of instructions that we're going to run it for the parent, and a block of instructions we can run it for the child.
If you say if you're the child, then perform this task, and the child does that task, but it wouldn't go to the den until the stuff, like, if you have, like, say, child will do this, right? It's not going to get to the den until, or like after.
The else?
Yeah, else until the child gets done with the stuff first, right?
No. Because now we're running the same thing twice. So the idea is this. Oh, do we have some work code here? Here we go. Perfect. Okay, so notice here in this section of in this code, this is a program, okay, and it's calling fork, okay. We have the fork call right here, okay. At that instant, right, when we execute that statement, what we do is you have this section of code here, and it says PID equals fork. Yada, 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 right? And then some stuff all the way to the end, okay? Right when we call fork, we take everything about this process and duplicate it. Okay? What's important here, though, is that they are now separate processes. They have their own memory, and they can change variables and things however they want. What's key here, though, is that when fork returns, it returns a different value for the parent or child. So there's a variable PID that it is setting to the what fork returns, right? So at that instant, we now have a difference in the 2 different programs. Because in the data segment here, right, there's a little area for storing PID. This will get some number, and this will get 0. Right? So now what do? If PID less than 0, an error occurred. That's bad. Okay. If PID equals 0, we're the child. else you're the parent process. So now, even though we're running the same code, when we get to that if statement, we'll branch and do different things. Okay? So this kind of takes care of that problem of, well, this block of code, the child has to get through it before it starts, evaluating the else. Actually, what happens is at the if, it'll find out where it needs to jump. But we now have two threads of execution now, two concurrently running processes. These instructions are getting executed at the same time, essentially, using context, using time slicing. Yeah.
But it says parent will wait for child to complete.
Sure.
But then why not just do it in this program rather than branching from working on?
Why? The parent's gonna wait here, right? Because this program doesn't do anything interesting. I could do whatever I want in here before I wait.
Okay. So a child and parent are doing stuff at the same time.
Maybe not. You may have a reason for not doing anything. For example, we can't spawn any processes on a system unless we have some mechanism for running these other things. And once you spawn, if you're a big process up here and you spawn something that's going to spawn other processes or whatever, you might not have to do anything. Okay? The key is you're not required to do anything in either process. Okay? All fork is doing is duplicating the process, returning a different number, and then you're welcome to do whatever. Okay? Just because we don't do anything doesn't mean that that's not a separate process. There are tons of processes on your system that probably don't do anything most of the time. Right? So we can put whatever we want in here. We could just wait and do nothing. Why do this, wait and do nothing? What if we spawn 2 children? I don't know. Then waiting for both does make sense. Right? We are still doing 2 different things. Right? And we're just the coordinator of those 2 different things. Okay? What if, depending on why we spawn that, we might have some mechanism for the main process in charge of killing those processes if it receives a signal of some sort. Okay? But the whole key here is that the process is just duplicated. That's where it gets the code. So what do you notice about this program that it does if you're the child? It calls this exec statement, right? Okay, anybody remember what exec does? It does execute. How does it do it, though? Okay, exec's very interesting in that it takes the current running code and replaces it with the program that you've called with exec. See how that's helpful in the case of fork? Because fork is running the exact same code that the parent was running. What's a real easy way to run a completely separate set of code? Load new code. So you run exec, and it will load up that new code and run it in the child's thread of execution.
So it's saying, go to this directory and
That file,
yeah,
in bin,
file. Okay.
grab ls, right, list, and load all of ls in place of me. In place of the...
I've just never seen that before, the exec statement. I've never heard of that. So.
Yeah, so that's basically just a call that says, run this program in place of me. Now there's other system calls where you can just run it and then come back. So you come back and then you can continue running your code.
I have a question about this over here.
Yeah.
If you're basically just making an exact copy of everything that's up there.
Right.
Then why doesn't it fork again?
Oh, because we got past it.
Oh, so you already passed it.
Yeah.
Okay.
Yeah, that would be bad.
Yeah.
if we forked but essentially you're at the exact same spot that the parent is, which is after fork.
I see. Okay. That makes more sense.
Yeah. I mean, the trick that the system does is it doesn't have to do anything in the child process, but what it does say is return value is 0. So that's the trick it's done, is returning 0. Whereas the parent, it just kind of looks like a regular instruction.
Just on that line, when it
This one?
calls, next line, the exact code there, the B,
Oh,
LS.
gotcha. Yeah.
Okay, in that case, does it say the specific file to run or something?
Yeah, that's the executable you're supposed to run.
Because after LS is a no there, so.
Oh, this is command line parameters and stuff like that. Like you could put a string in there that's -L for long listing or whatever. Yes. Oh, it means the instructions that are in memory that are these instructions. Wipe them out. Get this file ls, and load all the code that's in ls in place of it, and start running. Okay. So essentially, what happens is when we get to that exec, this is the parent, this is the child. The child gets erased, and LS's instructions go in its place. Okay? That's key because what's interesting about that is if you're the child, you never get past this line.
So it's totally gone.
Gone. Yeah. It's like all the instructions are taken out. Right? So you could have all kinds of, like even in this if-then block, you could have all kinds of instructions here, like format your hard drive and like do all kinds of nasty things here, and it'll never be seen because this wipes it out. Hopefully, actually, I think exec's behavior that if it can't execute, if it can't find that file or load it, it will return an error and stuff. So that'd actually be bad if you put all the format stuff there. Somebody could just make sure exec fails and make it do bad things. But the idea is that nothing after that gets executed because that code gets erased. Okay? This is the easy way to use fork because you don't have to go write another program to be the child process. I mean, you don't have to write more code in this program to run for the child process. You just write another program or find a program that does what you want the child to do. Okay? So questions on that? Okay. This mechanism is how all the processes, like on a Unix system, are started. Okay, they use this exact mechanism starting at init, process 1. You actually run an initial process called init, and it's in charge of going and forking and getting these other programs and running them, which will then go get other programs and run them, which will eventually get to like a shell that you as a user can log in and run your own programs using the same mechanism. Okay? And that's really all a shell is. A shell is a simple program that just does this, that does fork, that calls exec and stuff like that.
So it's forking probably thousands.
Yeah. So anything that's running on your system, right before that, a fork was called probably. So it should work. You need to make sure that fork is written well. Okay? So, I mean, that's the mechanism, and that's why we're doing that. That's what all this context switching and stuff like that gets us. Is this mechanism that we can do this?
Is there a flex set, something like that? Suppose the child is doing whatever in bin file, and after finishing, probably it's not written in this program anything, but it does show that it's done.
Yes. When you get to when you load a program, okay, what happens in that program we don't have any control over, right? The code that's inside ls controls what happens in that child program, okay? But we can get some results through this. This wait will return the status that the child returned. But in this case, right here, the status that's returned is the responsibility of ls. ls has to return a status of some sort, and we'll get that, okay? But that's really the only communication that comes back from a child, is the status returned by wait. Okay? We need a whole other mechanism if we want to do some sort of fancy talking between the child and the parent and that kind of thing. Okay? We need to do this stuff, and we use inter-process communication. And that's what we're going to see in a second. Okay? Now, there's a big difference between this and threading. Okay? The goal is the same, is to run two things at once. Right? Is run something here, and then the parent can run something else and then get the status from the thread or whatever when it comes back. But there's a major difference, and the major difference is this doesn't happen. Okay, this copying of the parent process for the child process. When you thread, you actually usually give the thread code to run. In other words, you'll create a function that is kind of the thread's work. And then you create a thread and say, here's your work, run it. Okay? We didn't do that here. We just said fork, right, with no arguments. So it just duplicated what it was doing. But with a thread, you say, I have some work for you to run. Here it is. Okay? And we don't get duplicated, right? It just runs in process. The thread does, the additional thread execution, right? So if we don't duplicate here, where's the thread going to store its values for its variables and stuff like that? Because when we fork, we now have copies, and we have a duplicate data area now that we can start writing values to. And we've seen already that they can be two different values. They are two different values once we start manipulating. Where's the thread going to store its data? If I take away this, where's the only place we can store data? Right here, right? So where does the thread store its data? Well, where the parent stores its data. Which is neat. Which is what makes threads a lot easier to program than processes. Because you don't use inter-process communication anymore. You can actually just use the memory. And store values, retrieve values, things like that. Okay? That's why threads are usually called lightweight processes. Because they don't have their own memory and all that good stuff. Okay? So, now we have a nifty mechanism for creating new processes. So what do we do with that? Well, this is just kind of going over what we said. It's duplicate, has the program that you're running loaded into it. And then exec can be used if you want to do what we saw in the example code, which is load new code in place of the child's code. You're actually welcome to load new code in place of the parent's code, if you want it as well. That usually doesn't work out quite as well, because the main reason that doesn't work out quite as well is because you lose stuff like the process ID of the child that you returned. And this new program you're running doesn't have anything, it couldn't wait for the child, because it doesn't have any knowledge of the child anymore. Okay?
So if
Yeah.
the parent process remembers the child's process ID, where's its process ID?
The parents, the system knows that. Its parent knows that.
Oh.
Right? Because somewhere along the line, something called this program, probably your shell. And then it goes down until you get to 1. And 1 is init. Or 0. I don't know which one init takes. But the first process gets it, and then everything else from there on out is known by the parent. There's probably a system call to get your process ID. But for the most part, you won't ever need it.
Yeah, I remember doing that, like making one sleep or something. That was an exercise.
Yeah.
Put it in the background.
Yeah, usually the sleep is just to take up time so that you can see the results. Because if you don't put any instructions in there, it'll have returned. And
That's what I was going to ask you. Is Yamako everything is finished?
what, Yamakra? I don't know if they saved the home directories or not. I imagine they did. No? Ooh, that's bad. Okay, because I had stuff on there too. But it's Qubit now, right? Isn't that what they created? Yeah.
I set it in my own
Man, I mean,
Some,
I can't believe they wiped out the directories
I
on
think they
that.
have it home somewhere.
Huh?
They can just delete the entire thing. I think they have it
Yeah, they
documented
can.
somewhere.
It's RM dash R / export home. Oh, really? Oh, so the home directories are still there? Okay.
wow, good news.
I need to.
Bunch of things there. And,
Like your-
my
like your-
personal computer is,
Your precious code that forks child processes and sleeps.
yeah, I did
Yeah.
for less
No.
sleep, man.
No, but I mean, actually, all the code that if you have the code from systems programming is, I mean, that's what we're doing in here as far as what code we see examples of.
Yeah,
So
it's
I mean,
been
some of this should
something
be
like-
like what you were doing there. Okay, so we can do interesting things here, like either exec, load another program, or do even more extravagant things like sleep, right? We can do different things here. And then once we exit, once the program terminates, that can be returned to wait. Okay, the status of that, because just like the status of anything you run, and like your return value when you run a program in the shell, right? In that case, the shell is the parent, and the return value from the program is the status that it got from wait. So here is a look. Okay, so here's a look at the tree of processes on Slayer. So they actually put a kernel process of the scheduler at process ID 0, and that's responsible for running init, which is process ID 1. These are actually, both of these, the page out and fs flush, those are system daemons that do things like, fs flush is probably files, it manages the file system to make sure that stuff's actually written to disk once it's put in cache and everything for performance. And then page out is probably a virtual memory type process. Okay. These two right here, these programs like this is a fuzzy area between what's kind of operating system and what's programs. Okay, because a lot of modern operating systems they don't do even some fundamental operating system things in the kernel. Okay, there are actually modern operating systems that do hardly anything in the kernel and run almost everything as userland processes. These are usually, I don't know if any of you have read anything about, kind of like design ideas of like microkernel versus monolithic kernel. Okay, microkernel, the idea is you write a very, very, very simple piece of core code that is the kernel, and everything from scheduling to file system management to paging and stuff like that is actually written as regular processes that do message passing to the kernel. Okay, what's the benefit of that? Well, the less you have in the kernel, the part that actually talks to the hardware, there's less space for bugs, right? There's less space where things can go wrong. Even more importantly, you get portability, right? If you change architectures, even whole chip architectures, you just modify the kernel and the rest should be straightforward as far as moving to the new architecture because they're all kind of up in user space. Okay, what's the drawback?
You rely on the other processes a lot, and you don't have the.
Right, but what's the benefit? Well, that code that's in the other process, somewhere in a kernel that doesn't use those, that similar code's running in the kernel, right? So like if you have a scheduler, and the scheduler runs in this process outside, if you don't run it outside, you still need a scheduler. So it's somewhere in there. What is the benefit of that kernel? What's special about that kernel of an operating system that's different from what like programs that you or I could write in user space? How does the kernel see memory? Yeah, well, hopefully ours see it as numbers too. What numbers?
Memory addresses.
Physical memory addresses is the key, right? I mean, it's seeing the actual hardware and interacting with the actual hardware. When you get outside of that, you're using, this kind of user space view of memory, which is more kind of abstract, right? So you have the kernel. The benefit is that you're right there on the hardware. So you don't go through all this indirection. It's faster. And things like that. If you're running outside of that, you're probably going through a lot of translations and things to actually get things. So doing that, you're probably going to be slower with a microkernel in a lot of ways. And there's big debate as to whether or not you're slower as opposed to monolithic where you write it inside the kernel. But one of the main benefits, again, is that you are portable. There's a very simple piece of code. You can swap different pieces of fundamental parts of the operating system in and out. You're very modular, okay? But you are more abstract. You're probably, you're farther away from the hardware and things like that for even fundamental kernel operations, okay? And then monolithic is where you just write everything in the kernel. Then you load it and then run it. And all of that stuff occurs inside the kernel. So all that code is responsible for making sure that nobody's accessing memory, that other parts of the kernel are accessing, and all that good stuff. Okay? And then there's stuff in between. Okay? This branch right here, off of this little piece, this is the kind of the user space, that like the user land where programs are running, like the regular programs are running. It starts it, and then we start spawning off all these sub-processes. Like these sub-processes are interesting in the fact that like these are so that users can log in. It's basically just a program that runs and waits for a user to give its login. So in this case, this DT login is a desktop login into X Windows. Okay, so that you can start a X Windows session logging in, say, at a terminal or a remote terminal. inetd is basically the internet networking server that runs that will spawn other things like web servers and, in this case, like a telnet daemon. Okay, what's a telnet daemon? It's nothing but a program that listens at a port and waits for people to come to it so that you can log in. Okay, and then eventually you get down to the point where you're running a shell. So in this case, C shell. Okay, and then from C shell, the user can log in and start typing in commands and run other things like ls, cat, emacs. Okay, questions on that? Okay.
So was that, you're saying that?
Why do you always wait until I switch the slide?
Sorry. It takes me a little while.
If you're going to ask the question, ask it when the slide's up. All right, go.
So, there's a desktop, somebody's logging in the terminal,
Yeah, somebody's already logged into the desktop
and then somebody's logging in over the web, is that what that means?
over telnet.
Oh, telnet.
Yeah. But we might have HTTPD down here, running web service, whatever. But yeah, at this point, looking at the tree like this, someone's already logged into both of those and has started running things.
Okay, right.
Like this one, like that's interesting that they're running Netscape over telnet, which is a pretty interesting feat because there would be no graphics output. Well, no, they could redirect the X output. So. But yeah, so at this point, it's already running. And then, again, from here, we're not limited by this, and it's not necessarily a line like this. So, for example, if you run an X session, chances are you'll have a C shell, and chances are there'll be other stuff running as well in your session. Okay, you'll have X terms or DT terms in the case of CDE, but you'll have other programs running here as well that also have the capability of spawning more. So this tree is really broad as well, not just deep. Okay. So, process executes the last statement. This is what happens. How does a process get done? Process executes the last statement, asks the operating system to delete it. Okay. You can, whether it's by explicitly exiting, calling the system call for exit, or just falling off the end of your program. Right. Your compiler will put in a done system call at the end, but it would be done. Output data from the child to the parent via wait. So again, this is the only mechanism we've seen so far for communicating between the child and parent, right? And that is returning status information from wait. Okay. And then after that's done, the process's resources are deallocated by the operating system. Notice this happens first, before this. That's important because if you deallocate your resources, all that information that was your status and things would go away and you wouldn't be able to return anything. Okay? So it seems like, pants first, shoes second, but this is actually very important, but it also causes a problem. Okay? What problem do you think that could cause? This ordering. Okay, I have to return my information to wait. In other words, return my status to the parent. After that, I will deallocate system resources. Anybody have any idea what problem would come up there? Anybody remember the term zombie in terms of systems programming and Unix?
The process is never killed. The child process.
Yes, but why?
It's still it's killed before the allocation of the.
No, it's not killed. If it was dead, we could deallocate it.
Process ID is gone before the
What process ID?
child process ID.
Ah. Here's the problem that occurs to create zombies is when a child is trying to report its status to the parent, but the parent's gone. Okay? And that occurs from this ordering, right? Because if I'm sitting there trying to return a status, I never get to this part, right? So what happens is I have all my resources still sitting there, not deallocated, and I'm still waiting to return a status to something that doesn't exist. That's bad. So what ends up happening is we're zombie. We're a child process, no parent, can't be killed.
But
We eat
you asked the question regarding those two lines, like which one?
Right.
I don't get the point about.
Okay, if I am returning status information, but I can't, what do I do then? See, think of these like instructions. Here. Right? This is where I deallocate resources. Instead of one, you could have return, return while returning status to parent is not successful. So what will I do? I'll sit there waiting to return my status information, and I never get to this call, which deallocates my resources. Okay? This is just an example, because all of this stuff actually happens after exit. Exit, and you want to return status and stuff. Okay, exit is kind of the other end of wait. Okay, so that's bad. So typically, though, how an operating system handles this is if a process dies, or there's actually multiple ways. In some operating systems, you can prevent zombies by doing what's called a cascading termination. Okay, cascading termination is when you what do you do? When any process dies, the operating system will go through and, it sounds bad, kills all its children. Okay? It goes through, and when that parent process is killed, it goes through and kills all its children. Well, what will it do to those children? It'll kill all its children. And it will go through and kill all the children it can find, and then we get back, and all of the resources below that part of the tree are deallocated. Okay, stuff like this doesn't usually happen in more modern operating systems because that would be bad. Well, I mean, VMS does stuff like that. Okay, but what typically happens in operating systems is children can continue to run beyond the parent process. Okay, but we need to take care of this type of mechanism still. So what typically happens is, like for example in Unix, if a parent is terminated while children are still running, okay, we need the children to have a new parent. So, who adopts them? This one does. Okay? Another one of init's jobs, okay, is to inherit any children that the parent process has gone away. Okay? What does init do with these children? All it does is says, I'll take your status information and I'll do absolutely nothing with it. Right? I'll accept your status information, throw it away, just so you can get to that next step of deallocating all your resources. Okay? So zombies happen when a parent process dies and somehow you prevented the mechanism of inheriting to another, to init.
So is there such thing as an orphan process?
No, and that's why there's not an orphan process, because init is always ready to adopt. So, actually, zombies could be considered orphan processes, but zombies sound more foreboding. Well, I mean, a lot of people, you can refer to an orphan process as something that's been inherited by init in a lot of ways, because init's not going to do anything with it. Okay. Oh, there, cascading termination down there. Independent and cooperating processes. The main thing that they're talking about here is really opening the door to processes communicating with other processes. Okay, we've already seen kind of some of the difficulties with this is that they get separated, all the memory gets separated, and we can't really manipulate each other's variables anymore and things like that. Okay, but we need mechanisms so that we can communicate between processes. And when you hear the term communication, you don't necessarily have to think of things like networks and things like that. Communication can be something as simple as being able to read a value in a variable that another process can change the value of. Okay, that is communication. Okay, so process cooperation, we can do things like information sharing. That's obvious, communicating information between the two. Computation speed up, the idea of running multiple threads of execution so that we can, if we have multiple processors, right, like a multiprocessing system, we can run multiple threads at once, and start to finish will get speed up compared to running them in order. Okay, modularity. Sometimes people use multi-threading not necessarily to increase performance. Okay, multi-threading can actually be helpful on a single processor system. How is it helpful? Or even in a single program? It can be helpful because sometimes multi-threaded or multi-process code, sometimes it's easier to write than sequential code. Okay, and that usually comes into play when that task switching between different tasks gives you the benefit of kind of keeping track of two different pieces of information, two different kind of ideas going at once. When I was showing you some of the examples of multiple threads and time slicing and things, I showed you that you can actually simulate most of this stuff with the sequential code by just kind of doing a little bit of one, writing the code to do a little bit of the other thing, writing a little code to do a little bit of the first thing, and back and forth, right? You can actually time slice kind of within your code. But it can actually simplify things if you just create two threads, let them run at the same time, and then sync up. Okay? So this modularity and convenience, you can actually sometimes write code easier by going multi-programming. Okay? And that seems counterintuitive because actually there's a lot of overhead in learning how to do multi-threaded execution. There's a lot more system calls than your just typical run through a sequence of instructions. Okay, so how do we get to these cooperating processes, these processes that can communicate with each other? Well, we need some mechanism of passing information between them. This is typically outlined with a very general idea in really multi-processing, networking, all these types of things, is the producer-consumer problem. Okay, when we're writing the mechanisms for message passing, okay, we have we're responsible for the problems that come up with producer-consumer. So the idea behind producer-consumer is you have two actors, right? A producer and a consumer. The producer is generating some sort of object, let's just call them objects, okay? And the consumer is getting those objects. So what kind of problems come up when we have somebody generating objects and somebody using objects that are generated by that producer? There's just some really simple combinations that could happen there, right? What's the ideal situation?
They work at the same rate.
Right, so producer produces something, produces an object, puts it down. The consumer comes over, grabs the object, and uses it. And every time that happens, every time the producer wants to produce something, it has a place to put it. Every time the consumer wants to consume something, it has an object there. What else can happen? From the consumer side, the consumer goes to consume. There's nothing there, right? So now there's a bunch of questions what should happen. Maybe not as intuitive. What can happen from the producer side? It produces an object. There's nothing to stop it from producing the object, right? But what's the problem it runs into? Nowhere to put it, right? So I'm the producer. I'm create an object and I'm about to put it down so the consumer can get it, but there's another object there. What do I do then? So those two situations, right, of the producer producing something and not being able to put it anywhere, or the consumer trying to consume something and there's nothing there. So what kinds of solutions, or at least let's call them protocols, should we follow, or do we have the option of following those situations? So I am the consumer, and I'm about to go, and I want to consume. So I go over to the shelf, and I'm going to get an object, and there's nothing there. What are my options?
Wait.
Okay. One of the first things I can do is wait. I can sit there, wait at the shelf. And then when an object shows up, then I grab it. Okay? There's some variations on that. How long should I wait? What's the easiest way? Just wait forever, right? You can sit there and wait, and you'll sit there and wait until we get an object. Okay? I can wait not at all, right? I can go up there, no object, walk away, go do something else. And then there's everything in between, right? I could wait a little bit, right? I could come over, wait for 5 milliseconds, and if nothing shows up, then I'll go do something else. Okay? And there's trade-offs to each, right? If I go there and I wait indefinitely, right, it may be that I never get an object and I never continue execution. Okay? One of the things about the idea of like not waiting at all, okay, is it's all well and good that if we don't wait at all, we can actually go and continue and do other processing. But chances are, if we're going over there to get an object, we don't have anything to do unless there's an object, right? So those types of kind of strategies, both or all of them, or combinations of those are usually going to be available because one's not better than the other. It's a matter of what would that process be doing otherwise if it wasn't getting this. If you can't do anything without the data that the producer is producing, you might as well just wait, right? Because you don't have anything better to do, right? All your other instructions might depend on the values in that object that was created. Okay. So we usually term these things, when you wait for something, that's blocking. Okay, or synchronous. You'll sit there and wait, and basically be in sync with the producer at that point. Okay, you're going to block. In other words, you are going to stay there and not continue with your execution until this call is successful. Okay, the other one, the asynchronous way of going and checking. If nothing comes back, you get null back for your object. Then that's asynchronous or non-blocking. Okay, Usually if you're non-blocking, you have some mechanism that can do something in either case, right? If there is an object there, then you get it, and obviously you're going to work on that data. If there's not an object there, then you'll probably find that out and do something else, whether it's you have other jobs that you can perform, or you report something back to the user, or what. Okay, but those are two different approaches. The producer has a similar problem, right? It goes to the shelf and it needs to put something in the shelf, but there's no place to put it. Okay, we have the same types of idea. We can block, not block, something in between. Okay, so if we block, what we're going to do is we're going to stop execution, wait there, and then finally put it in once the shelf becomes available. For the producer, why don't we just create a buffer on the producer to hold objects before the shelf is available? Does that solve our problem of blocking, not blocking?
For how long? What do you mean? How long are you going to fill out the buffer?
Right. Well, as long as there's space. So what have we done? Have we solved the problem? What I'm saying is by me having a buffer, a queue of some sort that I can put my items on, that once the shelf available, the next item in that buffer will go onto the queue, onto the shelf. Have I solved the problem of whether or not I should block? Okay, no. That's a good answer, and that's the correct answer. No is the correct answer.
What if there's never a place to put it?
Right. Here's the trick. We've just changed the problem, right? We've just made it so instead of waiting for the shelf, now we can be waiting for the buffer. We'll just make the buffer bigger. Well, however big you make it, when that buffer gets full, you're going to get the same problem of do I block or do I not block? Okay? The producer actually does have a slight variation on what it can do. What's another thing it can do when it gets to the shelf and there's an object there and it has its new object and no place to put it? The consumer didn't have this option. There's a spot on the table. There's something there. I'm carrying my bundle. Are my only options sit there and wait for the table to clear or walk away? I can clear the table, then put my bundle down, right? The producer has an additional option, and that is destroy what's in the buffer, right? The consumer doesn't have that because it's just grabbing, it's reading.
What about the consumer just leave the one phone?
What's that? Yeah. What happens if the consumer needs the object that was there? Well, bad news for that consumer because it's not going to get it, right? So if it's critical that that information's there, then you don't want to use that option, right? You don't want to destroy what's in the buffer. But sometimes what's in the buffer, some things are kind of only important depending on the timeliness of them. For example, if you are streaming audio over the internet, okay, and you're sending these packets with little bits of audio in there, okay, what if you're the next piece of audio that comes, right, and there's something in the buffer? Like real-time audio. I'm watching a newscast. And somewhere else video is coming in, and I'm the audio. Well, hopefully we've written our protocol so that we don't get messed up. You see how audio, like a real-time stream of some sort, data is only important if it's at the right time. In other words, if that stuff's still sitting in the buffer, it's already too late for it. Its usefulness is gone, right? Me going through a stream and playing video for you and then showing you, and then playing audio that's from 10 frames ago, It's no good, right? You want to destroy that data, put the latest data in there, and always have the latest. If you can't consume it, you don't get it, right? And I'll just keep giving you data as fast as I can so that you can kind of keep up with the stream. So I mean that's the trade-off of some of these real-time streams, but you get phenomenal performance compared to how much data you're pumping over that wire, right? If they can just compensate for those little gaps and things like that and smooth it out, then you have a good real-time streaming format. Okay? Same thing here. So all of them kind of have their place as far as why we would want to approach that producer-consumer with different strategies, right? Sometimes it's good to destroy data in a buffer. Sometimes it's completely unacceptable to destroy data in a buffer. Sometimes it's all right that a process is sitting there waiting for space on the shelf or waiting for an object to be produced, and sometimes it's not. Okay? But all of these mechanisms are usually involved. So we have unbounded buffer and bounded buffer. Okay? So bounded buffer, you have a fixed buffer size. The buffer is really there just to to help with the producer-consumer problem. But the difference between having a buffer size of 1 and the buffer size of 10 really is just in delaying the problem of what do I do when the buffer is full. Okay? A lot of times you have a bigger buffer because there's ebbs and flows of how fast a process is going. So having a larger buffer kind of smooths that out so you always have, when you're running a little faster, you can fill up the buffer, and when you're running a little slower, you can let it chip away at the buffer, hopefully so that you, by the next time a time that's a little faster, you can fill it up for the next time that you can't get everything produced. Okay, so that's what the buffer helps with, but it's still kind of a similar problem to one item in, you have to wait for the consumer to get it before you can put another item in there. Okay, unbounded buffer places no practical limit on the size of the buffer. How do we do that? Well, one way is to just keep growing the buffer every time we add an item to it. What will we eventually do? Right. We'll eventually just run out of memory. And then what will happen? We'll crash, right? We'll seg fault, we'll attempt to allocate memory that's not there, whatever, and we will stop executing. Okay? Another way to do unbounded buffers is that idea of destroying what's in a buffer. Okay? So, bounded buffer shared memory solution. We create a buffer with a particular size, and then we have an in and out variable. Okay? And in order to add stuff to it, we use that in and out to say where the buffer where the buffer starts and where it ends. Okay? And when you get to the point where the start and end are the same, your buffer is full. Oh no. Start and end are the same, your buffer is empty. Okay? But if the start is right after the end, that means your buffer is full. Okay? But a buffer is just like an array. So in order to really get the trick working is you have to make it a circle, a ring. So how do we make things rings when it comes to addresses? Huh? No, how do we make numbers into a circle? Right? If these are addresses 0 through 7, I can go 0, 1, 2, 3, 4, 5, 6, 7. Where should I go after 7? 0, right? So to make those numbers a ring, we just do modulo, right? We just do modular arithmetic and make sure that we go in a ring, and then we just keep track of the start and end so that we never go over and write over valid data in the ring. So the idea is that you start with both the start and the finish being the same spot. You write, and then you stop here and wait for what? Stuff to get consumed so that the tail can, so that the head can go. Right? So you do the snake chasing the tail type of thing. All right, so that's what we do. And here, the remove, the consumer side, we do the same type of thing. We go through the ring and pull pieces out, right? And then we're both kind of responsible for keeping the in and out variables updated. Okay. Now, one thing we do have to be careful of is that we can make sure that we read these values correctly and the in and out values, because they're kind of being used by both sides. Okay. In this case, we're actually fairly safe because in, right, we're modifying in on the producer side and we're modifying out on the consumer side. So we're actually not writing to the same variables, which is good because we don't have to worry about contention for that variable. So, and that's the basic idea. Again, all those things that we talked about, there are different strategies on what you do with this. You might be able to make a buffer that's destructive. In other words, if you are making that ring buffer where you write and write and write until you get back to the beginning, you have the option of saying, well, start destroying and keep going. And even though the consumer didn't consume those parts at the beginning of the ring, just go ahead and start overwriting them, right? So that ring you can make destructive. And all those different strategies we talked about, we can do with these types of mechanisms. Okay? Now, the big problem here, though, with that buffer is how do we make it so that two processes can access the same buffer, right? Because what we've said before is that when you create processes, they kind of get their own memory. We can't just pass a pointer to it, right? Because my view of location 100 in memory is different from your view of location 100 in memory, because the operating system has played a trick on us and made us both think that we have 4 gigs of memory sitting there, right? So we can't just say reference address 100. We need to have some mechanism of being able to reference the same data. Okay? So we do things with interprocess communication. There's a couple mechanisms. This is talking about a mechanism that's known as message passing. Okay? The other common way of doing interprocess communication is with shared memory. Okay? So shared memory, message passing. Most ways that we communicate between two processes are a variant of either of these. Okay? Message passing is this. The idea is you create links between processes, and then you can send and receive messages between the processes by using some sort of intermediate conduit provided by the operating system. This is often done using what's called mailboxes. Okay, a mailbox mechanism is really just a small little kind of buffer like what we saw, where we write a value to the buffer, we write a letter, put it in the mailbox, and then the receiver will come, check the mailbox, and pull the value out. Okay? So, how do we do this? The interprocess communication needs to provide two primitives, and that's send and receive. Okay? Chances are we're going to have some other parameters here that are necessary to know where we're sending and receiving. So if P and Q wish to communicate, we have these kind of requirements. They need to establish the link and then use send and receive. Sometimes these can be combined into the same call, but the requirement is the same. You need to know who's sending a message and who's receiving a message. Okay? Sometimes, oftentimes the sender definitely needs to know where to send the message. The receiver doesn't necessarily need to know who sent the message, just that there's a message waiting. Okay? But oftentimes it's the sender knows the receiver knows the sender. Okay? So the idea is establish a link and then exchange messages. Implementation of the communication link can be physical. Physical or logical, what they mean by that is just this message passing is just kind of the way that we use this communication. How it actually does it may still be common things like shared memory and things like that. Chances are, though, it's shared memory at the operating system level. There's a lot of different ways to do message passing, but to the programmer, we really just need to know how to send, how to receive, and then let the operating system handle everything else. Okay? And in fact, chances are the operating system is going to make a lot of decisions on how it handles the message passing to increase performance and things like that. For example, in Windows programming, you typically, when you want to communicate with another process, you basically just do a remote procedure call. And we'll talk a little bit about that, but you do a remote procedure call, and the operating system can actually determine whether that remote procedure call is going to a process on your machine or on a remote machine. If it's on the local machine, it'll actually translate your remote procedure call into what's called an LPC, which is a local procedure call. Okay? So even though to you, the programmer, it looks the same, I send a message and receive a message, to the operating system, it's changed the mechanism by which it does all that the communication. So this establishing of the link, that's a big job of the operating system. And the programmer just sees it as sending and receiving messages using this interprocess communication mechanism. Okay, so how are links established? Can a link be associated with more than two processes? And how many between how many links do we need or can we have between processes? All of these are different implementation styles of doing inter-process communication, and they each have their pros and cons. How are links established? The idea of maybe I send it to process IDs as some sort of address. There's also another mailboxing mechanism where you don't talk directly to the process ID. You might name a mailbox of some sort that you both agree on. Okay, this has the benefit of the fact that process IDs change depending on when you run a program and whatnot. Okay, but we need some sort of addressing system so that we can get from one process to another. Because if you're a program running on a system, there's tons of processes going on there, and you need some sort of way of distinguishing which is which. Can a link be associated with more than two processes? The idea of a producer and a consumer, that's hard enough. If you start adding in different variations on this, like for example, producer and two consumers, okay, you start introducing new problems of what if both consumers are waiting and I create an object and put it into the queue? What will happen? Okay, do they both get it? Does the first one there get it? Does the last one to listen to the mailbox get it? Who knows? But those things need to be established so that the programmer knows what's going to happen. Okay? A lot of times, in some systems, you might say that you cannot have more than one producer and one consumer. Okay? That obviously simplifies a lot of the creation. How many links can there be between every pair of communicating processes? Can I have multiple links between process A and process B? Okay, depending, and this can also be very dependent on your addressing mechanism, right? If you're just pointing to a process by using its process ID, how do you distinguish between the two links, right? Process 1 talking to process 2 will always look like process 1 talking to process 2. There's no way to say what's another link that I'm using between the two. Like, so for example, this type of problem is solved in socket programming by using things like ports, right? Where you can talk to another system based on its IP address, but then you can talk to different programs on that system using port numbers. So that's an example of where two systems can talk to each other with multiple links between any two systems. Okay? What is the capacity of a link? Okay, we run into this buffer idea. What happens if you're about to put a message and there's no room? Also, what is the size of the message? Right? Do I have fixed size messaging? What's the benefit of fixed size messaging versus dynamically sized messaging? If you're sending dynamic, if a message is always 112 bytes,
The other side knows what to expect.
right? How long should I read? Well, I read 112 bytes and then I'm done with the message. If it's variable size, what do you need to send also? The size, right? Or some sort of terminator or something. You have to have some sort of overhead for saying, here's the start and here's the end. One's more complex but more flexible. One is, more straightforward, but you're restricted to particular message sizes. Okay. Then you can also have other mechanisms where they're fixed size messages, but one of the message types is, hey, go look at this other spot for a variable size message that I'm sending. Okay. For example, Windows XP's LPC uses a mechanism like that, where it's typically fixed size messages, and then you can kind of do these kind of pointer messages, which point to an area of shared memory where you can grab bulk data that's of variable size. Okay, so link unidirectional or bidirectional, right? If you have your mailboxes that just go in one direction, then if you want two plus to talk to each other, you need bidirectional. You need to create one for sending and one for receiving. Okay, and that also relates to how many links can there be between every pair of communicating processes? You might say I can only have one, but directions involved as well. So that means you could have two links, but one has to be one sender to receiver, and the other one's receiver to sender. Okay, so some communication methods. Again, a lot of these things are all kind of interrelated. It's really up to the operating system to manage these details as to how we do these things. So when I talk about things like message passing, right, with these types of mechanisms, all these message packet passing mechanisms, that might be done using shared memory. Okay, and when I talk about shared memory typically can't really be done with message passing, but the idea is that it's up to the operating system to do the details, but the two major mechanisms are shared memory and process communicate and message passing like this. So, how do we do message passing? Is a detail of the operating system, and these are two kind of major models of how processes can communicate with each other. The first one, what do you notice is the difference between these two different modes of message passing? The shared area on this one doesn't have like a separate part here. This one's going through the kernel. Okay, that's the major thing, is that in this one, you are communicating with the other process by you pass a message to the kernel passes a message to the other process. That process might be able to respond, or you might set up bidirectional links. Okay, but this is a way for them to talk to each other because they both know the kernel, and the kernel's in control of everything, so it can pass values between. We can't talk between these two directly necessarily because they both don't have any things in common. The whole purpose of our operating system was to make these processes look like they have their own machine. Right, there's no link between them. So what they're doing is they're using the kernel to mediate the communication between the two. Okay? This is another method which is a little trickier in the sense that you break that rule of processes just having their own view of everything. And you do something like have process A and process B, the operating system will grant them an area that's in common. Okay? So this shared memory type of idea is process A and process B will both kind of agree upon a section of their memory that they're going to have the operating system they're going to have the operating system merge those two areas of memory to be one area of memory. So what you do is, so for this buffer, I want to create a shared memory segment from the operating system. So for example, process A will say, I'm setting up this buffer of my memory to be shared between us. Operating system, share this memory. Operating system will grab that address, right? Look through its memory manager and say, okay, here's the area of memory where that is. I'm going to make it so that process B can go to that same address and update the same memory as process A. Because normally, whenever you go to an address, the operating system tricks you. It goes to that address, but it actually maps it to some physical address or virtual memory somewhere. Okay? In this case, what it's doing is it's saying both processes are allowed to address this particular area, and it's the same page of memory, of physical memory. So if you change a value here, the other one will see it. Okay? So these are the two major types of ideas. Is you do message passing via the kernel. Sometimes you might be able to set up some mechanism where message passing is done directly between the processes, but
What's the best way?
there is no best way. Right? I mean, there is no best way. Right? These each have kind of their reasons for. I mean, they each have their purpose in the operating system. Message passing, depending on the parameters of how big how much with the size of messages, whether you have variable length messages, how do you, what is the format of the message as far as can I pass complex data structures? Shared memory, how you address the shared memory, whether you want another process having that much access to memory that you're using. These are all different issues. So both of these communication methods are usually available in all operating systems. So each has their purpose, and you use them for what you're trying to do. And most of the tasks that we have, right, these methods are popular because most of the tasks that we have follow kind of one of these models, right? If we're two programs working on the same buffer, same area of memory and things, and we need all the data structure and all that stuff, we want all that running the same, shared memory works great, right? If we're two processes, what if we're written in different languages? We have different ideas of what data structures look like. Well, message passing might be better because then we can load up our own data structures and things like that. So they all have their kind of their purpose, okay? But the key is you want to know kind of some of the pros and cons here. Message passing is typically easier to do because there's these fixed kind of ways of talking between the two. It's mediated by the operating system, and everything's very clean. Shared memory it's just memory sitting out there. Now you're responsible for every all the stuff that goes on in there. So you should kind of know that one is kind of fast and loose, shared memory, do whatever you want, just write to these pointers and you shoot yourself in the foot, right? Whereas message passing is very, very rigid communication. You have to have well-formed messages, send them between, but I'll take care of everything and I'll make sure that nothing breaks. Okay?
Is the kernel say whatever suppose process is sending until process B is ready to pick it up? It's the same mechanism we were talking
We have all those options still. So the operating system may provide different message passing options of I'll buffer it for you. You have to buffer it. I'll let you store. Your book has some stuff on, like, for example, a mechanism where you can have a buffer plus one, and the plus one is kind of you can only have one of the plus one in at a time. That's kind of the buffer's full, but I just want to put this one message here so that I can go do something else. So normally, if the buffer's empty, you can keep adding messages as much as you want. But then once you get to that top, once one's in there, you have to block. There's no way to do anything else if you put that kind of one last fire forget message in there. So all these mechanisms are still available. All the things that we're talking about. This is just talking about the model by which it works. Okay. We talked a little bit about that. Indirect communication, the idea of using these kind of separate mailboxes so that we can agree upon a name mailbox that we're going to go to. And this name mailbox might be a system name that the kernel gives it. I don't know if any of you remember from systems programming, there's the idea of pipes, right, is a way to talk between two processes. There's the idea of name pipes and unnamed pipes. Okay? Unnamed pipes, when you set those up, what you do is you actually use process IDs. You actually get the process ID of where you want to, the processes that you want to establish the pipe between. So you create that pipe and then you start talking to each other through the pipe. You put messages into the pipe and they can read messages from the pipe. Okay? Name pipes are done outside of it, usually called name sockets, where you actually create a FIFO file in your, it's not a file, it's a special file called a FIFO, first in, first out, on the file system. And then you load up your programs and then you actually open those files and then you can read and write to the file. And it's not a file, it's a buffer that's handled by the operating system. Familiar at all? That's name pipes. And then the one where you do the process IDs is unnamed pipes. Okay. Well, trust me, it's there. Okay. So this is this idea of sending to a process P, receiving from process Q. That's the idea of kind of like an unnamed pipe where you're directly talking between the processes. Here you kind of the name pipe idea is the mailbox is that FIFO that you created that has a name that you can open and interact with.
But they both have to deal with that file.
What's that?
Both processes have to access that.
Yeah, so in other words, the name of that file is the name. In other words, is this indirect mailbox name. So yeah, you both have to open the same file. One of you for writing to it, one of you for reading to it. Okay, and if you don't know the name of the mailbox, you can't talk. So that idea of creating a FIFO outside, that's something that the operating system facilitates, creating those outside. But you also have the system calls to create those within a program, and that's another way to do it. But the idea here is that instead of using process IDs, which are kind of hard to get at from within programs sometimes, especially if you're two separate programs, the idea is use, with at least FIFOs, with this name types idea, is that you're kind of using the file system as a directory for finding two different processes. You guys agree upon a location and a name, and you put a file there, and then that's your way of finding each other. Whereas finding each other with unnamed types or direct communication is getting the process ID. Okay? So this idea of if we have mailbox sharing where we might have multiple consumers and multiple producers, you need to answer these questions of who gets what, if there are two people listening, and things like that. You need to make sure that you're not duplicating messages if they're not supposed to be duplicated, and all that kind of thing. Synchronization, we talked pretty extensively about this, about blocking and non-blocking. Blocking is synchronous, non-blocking is asynchronous. And then you have all these different ideas of zero capacity. Zero capacity is the idea of a shelf with one slot in it, right? Actually, this is a little bit different in the fact that there's no shelf. Okay, zero capacity means that there's no shelf, so that means that the producer has to block until the consumer consumes it. The consumer has to block until the producer comes with the object. So that's why this is called rendezvous buffering, because both of you have to be sitting there with the call for sending and receiving at the same time, otherwise wait for the other one for any communication to happen. Okay, then in other words, the operating system is saying, I'm not holding any of your data, right? You have to be here, you have to be here. I'll do the copy between the two of you, but only if you're both ready to do it, right? In other words, for every amount of memory that you're, getting rid of that object, it's the consumer's responsibility to store that so nothing gets lost. I'm not going to do it. Okay? Bounded capacity and unbounded capacity. Sender never waits, but nothing's infinite, so either you have to have some sort of destruction of messages in the buffer or you need to crash because you run out of memory. Okay? Bounded capacity is anything from 1 to any arbitrarily large number is bounded capacity. That idea of no matter how big you make the buffer, you're just delaying the problem of what to do once the buffer is full, but it can help with this idea of sometimes you're running faster, sometimes you're running slower. Client-server communication. All of this stuff that we've been talking about, this message passing and things like that, a lot of this is abstracted to the point in most modern operating systems so that it's abstracted to the point where all these things that we're doing to talk between two processes, the processes aren't necessarily running on the same machine. Okay, so we have the idea of sockets, right, and using sockets to do communication over Internet Protocol, TCP/IP. This is typical networking stuff. Okay, same idea is we're just talking. It's inter-process communication, but one of them is a server running on a machine on the network, and then the other is a client running on your local machine or whatever, and they're talking to each other. So it's the same idea. The difference being is that like these mailboxes and things that we're talking about, they go over network. Have the same typical kinds of problems of what do we do as far as blocking, non-blocking, things like that, buffering. Remote procedure calls. Remote procedure calls are a mechanism available on most operating systems so that a machine can call a procedure that's to be executed on another machine. So the idea behind remote procedure calls, and I'm going to talk about this and like remote method invocation, RMI. These two are very similar. They're just the difference between procedural programming and object-oriented programming. Okay, procedural programming, you have functions that you call, pass them data values, and then they'll spit data values back out at you, right? Object-oriented programming, you create objects, they have data and methods. You manipulate methods to manipulate data in the object, and by changing the state of that object, you can use the state of that object like the data of procedural languages. Okay, so the two ideas behind this are we're still doing things like calling functions and calling methods. The difference is that once we call it, it actually executes on another machine. This is helpful for things where the method or function that you're calling might take a long time and you need a more powerful machine to run it. It might access data that's residing on another machine, who knows. But the idea is the same in both of them. The operating system or the RPC mechanism, what it will do is it will give the client, the caller of the function or method, it gives them a stub of the method or function. In other words, it's a function call with no body. Okay? So when that function call is made and passed parameters or passed an object, instead of it running on that machine, this stub will tell the operating system, go find this other machine and run this same function there, get the results, and come back. Then what I'll do is I'll return that value as the return, that value or object as the return of this stub that the client called. Okay, that's the idea behind RPC or RMI, remote method invocation. Okay, the idea is that you run a function, it executes somewhere else, and you get a result. Okay, so the biggest problem with doing RPC and RMI, okay, is the fact that in order to run these functions or methods, typically you're passing values to it. Okay, otherwise it's not really fun that you can just run the same thing without any kind of input from you. So in order to give your input to the function or to the method, one of the big problems that has to be solved by RPC or RMI is marshalling. Marshalling is the idea of taking this input, putting it into some intermediate value, sending it to the other machine, taking it out of that intermediate value, and then passing it to the function. Okay? With remote procedure calls, it's typically these different integers, string, characters, and character arrays and stuff like that you're sending to the function. So it just needs to take care of things like, I don't know, like for example, if you're sending an int from one machine to another, you might have to change the endianness of that int because it's running on a, like a PowerPC over here, and then it's going to run on the actual invocation is going to be on a Intel machine over here. Okay, so endianness. Does everybody know what endianness is? Endianness is a way of endianness, E-N-D-ness, E-N-D-I-N-E-S-S, E-N-D-I-A-N, Endian, E-S-S. Endianness is whether or not the most significant number of, or bit of a number comes first or last. Okay? If I tell you 100, oh, let's do it easier. If I tell you 10, okay, that can either be 2 or 1, right? If I tell you 10, if the first bit is the biggest value, the most significant bit, then that's 2, right? But if it's 10 and the smallest bit comes first, that's 1, right? We're used to reading things as big endian, right? Big end first, right? Left to right. So 10, the biggest number is the left. Okay, computers can do it either way. So that's a problem that marshalling solves, is the idea that maybe we'll switch which significant bit comes first. So it needs to mediate that. With RMI, it's even more difficult because now we're not just marshalling integers and characters and things like that. Now we might be marshalling whole objects. Okay, and that becomes more difficult. But the idea is the same. When I'm about to invoke a method of an object, it's only a stub. We go across the network or to another machine or to another process. We invoke it over there, manipulate objects, manipulate values, send them back, and then we get the results. Okay? Sometimes this might just happen on the same machine. Okay? And that's a very powerful mechanism for communicating between two different processes on the same machine, because again, all of this is solving the same problem. Processes don't have the same memory. Processes don't have any way except through the operating system to communicate with each other. Okay? And it might be something as rudimentary as writing to a file and then reading from that same file with another process. But these are all the mechanisms that the operating system provides for two processes talking to each other. Okay? Otherwise, they're independent. They don't care about each other. They just run on their merry way. For example, all my processes probably independent from yours. We don't need to do any inter-process communication or anything like that. Okay? All of your processes that you're running, chances are some of them are interested in some of the others. Okay? So, processes, done. Questions? Okay? On this chapter, concentrate on things like all the stuff we learned about things like context switching, multiple processes running on a machine, what kind of issues we have with them trying to get at the same input, output, and all that good stuff. Concentrate on things like the ways of communicating between processes, everything from the simple shared memory to message passing to these more complex message passing like what we just saw with RMI and RPC. What else did we cover in this chapter? That's about it. Those two are the big things. Oh, and in these communication methods, I tried to repeatedly talk about this idea of synchronous, asynchronous, blocking, non-blocking. How do we manage the buffers? Because that's really the issue that we need to solve at the operating system level. And then a more simple idea is this idea of a tree of processes, each spawning the other, understanding this phenomena of using fork. So those are the kind of the big things. Okay, the low-level details, those medium-level details of of the process tree, and then being able to communicate between completely independent processes. Okay. Homework due Tuesday, preferably online.